Surabaya. So my project investigates a new method to increase bacterial cellulose production in Acetobacter pseudomonas. Over the past years, many research has focused on this material because of its versatility and its implications to many different purposes. Also, bacterial cellulose has a remarkable potential to be developed in many places in Indonesia because it could be fermented from coconut water. The problem with this material is that it has a low yield and high production cost. And there has been a lot of attempts to be able to increase the yields. However, most studies has only focused on altering the culture media or combining different kinds of carbon and nitrogen sources, but this has only been met with limited success. And a few have also tried to genetically engineer the bacteria, but this of course required a lot of expertise and also sophisticated knowledge on this precise gene that controls cellulose synthesis in Acetobacter pseudomonas. I was inspired by Sarah Bowles' research, which uses artificial selection to increase lipid production in microalgae. And I was interested to see if the same method could be applied to Acetobacter pseudomonas to increase cellulose production. So artificial selection is a form of applied natural selection, basically, which uses the genetic diversity that occurs naturally. And then what we do is to create an environment, which is why it's called artificial. It is us that creates the environment in which we select for a certain phenotype or individuals that have the certain trait that we want. And in this case, I want to select for Acetobacter pseudomonas individuals that has an overproduction of cellulose. I hypothesized that if I treat a certain population of Acetobacter pseudomonas with sodium hypochlorite at certain concentrations, then it would select for the mutants that confer resistance to sodium hypochlorite. And these resistant mutants possess the ability to overproduce cellulose. Before I did the selection process, I have previously determined that I will be using 15,000, 20,000, and 25,000 ppm from the selection curve that I have plotted before. I then replica plated a master plate onto the treatment plates containing different concentrations of sodium hypochlorite. From there, I then isolated 3 random colonies and estimated the amount of cellulose produced through a spectroscopic assay based on congruent binding using a spectrometer that I have built myself. Because of the current circumstances of the pandemic, I had to build a spectrometer using materials that I can find at home. To measure the absorbance, I put my samples on a cuvette, and the visible light from the LED will pass through the sample and be diffracted by a diffraction grating I made using a DVD disc. It will then be captured using a webcam and connected to a software called Spectrograph, where I can analyze the spectra and measure the absorbance at a certain wavelength. For this, I used 502.8 nanometers to measure the absorbance of Congo red in acidic conditions. After I acquired my absorbance measurements, I then calculated my results using the formula shown here. So from all of my experiments, I calculated a few results. One, I was able to observe the mutation frequency that arises on each sample. Mutation frequency is basically the number of mutant colonies that arise per the total number of colonies that grows on the control plate. And this is the results of my Congo red assay. It is apparent that group B, which was resistant at 20,000 ppm, shows a 1.2-fold increase of cellulose productivity than the wild type, which hasn't been treated with sodium hypochlorite. However, the interesting thing is that this was not the case for group A and group C, which was resistant to 15,000 ppm and 25,000 ppm respectively. But overall, the data indicates that my hypothesis was true for the case at 20,000 ppm, and this data was significant and has a p-value of less than 0.05. From my project, we can conclude that first, the appropriate concentration to select for resistant mutants in Acetobacter pseudomonas is 15,000 ppm and 20,000 ppm in the case on solid media. And second, the mutants that were resistant to sodium hypochlorite in Acetobacter pseudomonas could be successfully isolated. And third, there was a significant increase on the samples that were resistant to to 20,000 ppm of sodium hypochlorite. And of course, my research has several limitations, such as I did not mutagenize the acetobacter culture prior to selecting the individuals, and I only did my experiments in triplicate, but the reliability of my data could be increased if I did more replications during the process. In the future, I would like to test if a multi-step selection would be able to increase the cellulose production even more, and whether there is an overexpression of enzymes or molecules such as the cyclic PGMP. But the most exciting part about my research is that it explores a method which has never been applied before to the bacteria Acetobacter, and this allows us to manipulate the organism without having to genetically engineer or insert a foreign gene into the organism. This makes it possible for amateur researchers or home growers and entrepreneurs who wanted to perform this method without sophisticated knowledge on microbiology. At the end of the day, I hope my research could contribute to the study of Acetobacter and its responses to sodium hypochlorite, and could also be a starting point in making bacterial cellulose more feasible as a biomaterial. I'm very open to questions and suggestions, so feel free to reach out if you have anything to discuss about my research. Thank you all for listening. Have a great day. Assalamualaikum warahmatullahi wabarakatuh.